Good morning all. This is Dr. D. Khalandar Basha, working as Associate Professor in the Department of Electronics and Communication Engineering, Institute of Aeronautical Engineering, Dundigal, Hyderabad. Today we are going to discuss the ARM architecture and the registers of ARM processor under the course Microprocessor and Microcontrollers. The slides are prepared by referring the textbook ARM System Developer's Guide, Designing and Optimizing System Software by Andrew N. Sloss, Dominic Sims, Chris Wright, publication Morgan Cookman Publications. The figure shows the data flow model of the ARM processor. The ALU will accept the two data. One operand we are going to be placed in RN register. The second one we are going to be placed in RM register. The RM register contents are given for barrel shifter for pre-processing. Whatever the data obtained, that will be passed as second argument. Depending upon the ALU results, the data will be stored in the register file. The data which we are sending as operand, either it may be a sign extended that will be read from the register files, that is R0 to R15. Apart from ALU, it is consist of MAC unit, which is multiply and accumulate unit, where we can perform multiple multiplication with addition will be done by using the MAC unit. So these two are parallel, can do the things. Next, the instruction decoder will decode the instruction of the ARM processor. Depending upon the decoding, the various functions will be carried out by the processor. For every time, the next instruction will be fetched from the address register. The address will be placed to the concerned location. The ARM core as a functional units connected by the data buses is shown in figure 1. The figure shows the Vanuman implementation of the ARM data items and instruction share the same bus. In contrast, the hardware architecture implementation ARM will have two different buses. One is for data, the second one is for code. Whereas in the Vanuman architecture, we are going to have a single data bus through which the instruction information as well as data information will be communicated. The data enters the processor core through the data bus. The data may be an instruction to execute or a data item because of the Vanuman architecture. The instruction decoder translates the instructions before they are executed. Each instruction executed belongs to a particular instruction set. The ARM processor, like all RISC processors, used a load store architecture. This means it has two instruction types for transferring data in and out of the processor. The load instruction copy the data from the memory to registers of the core, and the store instruction will copy the data from the register to memory. The reverse operation. Load instruction will copy the data from memory to register, whereas store will copy the data from register to memory. There are no data processing instruction that directly manipulate the data in memory. Thus, data processing is carried out only in registers. Data items are placed in the register file a storage bank made up of 32K bit registers. Since the ARM core is a 32-bit processor, most of the instructions treat the registers as holding the signed or unsigned of data of size 32-bit size. The sign extent hardware converts the signed 8-bit data and 16-bit numbers to the equivalent the 32-bit values as they read from the memory and placed in a register. The ARM instruction typically have two source registers. One is R1, that is RN register, and RM register. The register RN contents will be directly fed to ALU, whereas RM register contents will be sent directly, or we can go for pre-processing through barrel shifter. And a single result of the destination which is in RD. Total three kinds of registers will be there: RN, RM and RD. RN, RD are the input register, whereas RD you can take as the output register. The source operands are read from the register file using the internal bus A and B respectively. The ALU or MAC unit, that is multiply accumulate unit, takes the registers RN and RM for the buses A and B and computes for a results. The data processing instructions, so write the result in RD directly to the register file. Load and store instructions use the ALU to generate an address to be held in the address register and broadcast to the address bus. One of the important features of ARM is that the register RM alternatively can be pre-processed in the barrel shifter before the data is sending to the ALU. Together, the barrel shifter and ALU can calculate a wide range of expressions and addresses. After passing through the functional unit, the result in RD register is written back to the register file using the result bus. For load and store instruction, the incrementing updates the address register before the core reads or writes the next register a value from R to the next subsequent memory location. The processor continues executing instruction until an exception occurs for changing the normal execution flow. The ARM processor provides a general purpose and special purpose registers. The general purpose registers had either a data or an address. They are identified with the letter prefixed to the register file. In ARM processor, there are 16 active registers, out of which 16 are data registers. 2 registers are program status registers. All the registers are of size 32-bit size. The 16 data bus registers will be considered as from R0 to R15. The ARM processor has 13 registers which will be assigned for a particular task or a specific function through the registers, that is R13, R14 and R15. Out of the 16 registers, R0 to R12 will be used for general purpose, whereas R13, R14, R15 will be used for a special purpose. They are frequently given different labels to differentiate them from one another register. In addition to the 16 general purpose registers, we have 2 special purpose registers. They will call as CPSR register and SPSR registers, which will call as CPSR stands for Current Program Status Register. SPSR stands for Saved Program Status Register. In ARM processor, the following registers are available for accessible in any processor mode. We will see what are the various modes of operation we are having for ARM processor. 13 general purpose registers, they are from R0 to R12. R13 register is a stack pointer SP. R14 is a link register, that is LR register. R15 is the program counter PC. Apart from that, we have one application program status word, that is APSR. So the figure shows the available registers in user mode. R0 to R12, 13 general purpose register, 3 special purpose registers like stack pointer, link register, program counter. Apart from that, the status register, which is current program status register, CPSR. Figure 2 shows the active registers available in user mode, a protected mode normally used when executing programs or applications. The processor can operate in 7 different modes. Whatever the registers which you have placed in the diagram with the shaded region, identify the assigned special purpose register. R13 is traditionally used as a stack pointer and store the head of the top of the stack in current processing mode. R14 called as link register LR and is where the core puts the return address whenever it calls a subroutine. R15 is a program counter which contains the address of the next instruction to be fetched by the processor. These are the registers available in user mode from R0 to R12, R13, R14, R15, CPSR and SPSR if it is in abort mode. Whereas in the remaining modes, the banged out registers in the user mode we have R13, R14, FIQ mode R82, R14 and SPSR are available. In IRQ mode, R13, R14 and SPSR are available. In SVC mode, R13, R14 and SPSR are available. In UNDEF mode, R13, R14 and SPSR are available. This will call as bang out registers. So in detail for each and every mode, in the user mode, we can see R0 to R15 as general purpose as well as CPSR. Whereas in FIQ mode, the user mode, that is R0 to R7, R15 and CPSR can be used. Whereas R8 to R14 and SPSR are reserved for FIQ mode. In IRQ mode, the user mode can be used R0 to R12, R15 and CPSR. The IRQ mode will use R13, R14 and SPSR. In SVC mode, the user can be used in the user mode for the registers R0 to R12, R15 and CPSR. Whereas R13, R14 and SPSR are reserved for SVC. In UNDEF mode, the user mode registers are from R0 to R12, R15 and CPSR. R13, R14, SPSR are used for UNDEF mode. In the abort mode, R0 to R15 and CPSR, R13, R14 and SPSR can be used. For abort mode, R13, R14 and SPSR will be used. Remaining registers will be used in user mode. So this you can consider the upper, that is from R0 to R7 we will consider as thumb state low register. The rest of the registers we will consider as thumb state high registers. Depending upon the context, a register R13, R14 can also be used as a general purpose registers, which can be particularly useful since these registers are banned during a processor mode change. So, however, it is dangerous to use R13 register as a general purpose register whenever there is a processor running any form of operating system, because of operating system often use R13 as a valid stack frame. The next register is current program status register, that is CPSR. The ARM core uses CPSR to monitor and control internal operations. The CPSR is a dedicated 32-bit register and reside in the register file. The CPSR is divided 4 fields, each of 8-bit wide, flags, status, extension and control information. In current design, the execution and status field are reserved for further purpose. The control field contains the processor mode, state and interrupt mask bits. The flags fields contain the conditional flags. The figure 5 shows the layout of general purpose program status register, where from the bits 25 to 31 we are going to have conditional flags, overflow, carry, 0 and assign. Whereas bit 0 to bit 4 will use the processor mode. Bit 5 it is for thumb mode. Bit 6 and bit 7 it is used for interrupt mask. Some ARM processor cores have extra bits allocated. For example, the J bit, which can be found in flag field, is only available on Jelly enabled processor which execute 8-bit instructions. It is highly probable that future designs will assign extra bits for monitoring and control of new features. The N bit indicates it is for negative flag, records the 32 bit of the result flag setting operation. Z bit is for it is 0 flag. If the result of any operation is 0, then the Z flag will be set to 1. C it is for carry flag. It is unsigned overflow for addition, not borrow for subtraction and shifting operation. Overflow flag, that is V, which records signed overflow for flag setting operations. The Q bit it is for saturation flag. Certain operation set these flags on saturation. The J bit it is indicate the Java execution. When the Java execution is taking place, the thumb field should be equivalent to 0, that is T is equivalent to 0. Use the BXJ instruction to change this particular bit. RES fields it is for reserved for future expansion. The software should preserve the values in these bits. The GE3:0, a 4-bit allocated for SMID greater or equal flags. The bit E, it is for data endian, either it is little Indian or big Indian. If A bit is equivalent to 0, it is little Indian. If B bit is equivalent to 1, E bit is equivalent to 1, it is big Indian. The next bit, which is A, this is for disabling the data aborts, which is nothing but memory violations. The next bits are corresponding to interrupt I. This is for disabling the interrupt request which are of low priority, or we can call our normal interrupts. The F bit, it is corresponding for fast with high priority interrupts. To disable, we can configure this bit. T bit, it is for thumb state. Whenever T is equivalent to 1, thumb instructions can be executed. When T is equivalent to 0, the ARM will be in ARM state. Use of the BX and BLX instructions to change this particular bit. The last bits, that is 5 bits, bit 0 to bit 4, will be given for the mode of operation of the ARM processor. The various modes we can have like abort mode, fast interrupt request, supervisor mode, system mode, undefined mode, user mode. For this one, the bits are on mode will be configured in this fashion as we are seen in the table. Now, user mode. The user mode means it is a regular program that can be accessed, the resources they have, all the permissions. FIQ, it is for fast interrupt request. The processor goes into the FIQ mode when handling the fast interrupts. IRQ, in this mode, the processor will enter into the mode for handling the normal or regular interrupts. Supervisor mode, this mode allows the program to operate at a privileged level. Monitor mode, if you have a ARM processor with security extension, then this mode is used to monitor the system. Abort mode, if a user mode program try to access the memory, it is not allowed, then this mode is entered to let the operating system intervenes and either terminate the program or send the program a signal. Next, hypervisor mode. In this mode, it is a optional ARM extension which allows the virtual hypervisor run at a more secure level than the operating system for visualization. Undefined, it is a user mode program tries to execute an undefined or illegal assembly instruction. Then this mode is entered and the operating system can terminate the program and send the signal. System mode. In the system mode, the operating system at process a run that operating system consider a part of itself run at this level. The processor modes. The processor modes determine which registers are active and access right to CPSR register itself. Each processor mode is either privileged or non-privileged. A privileged mode allowed full read and write access to the control field of the CPSR, whereas in non-privileged mode, only read allowed for CPSR but still allows read-write access to the conditional flags. There are 7 processor modes in total. 6 are privileged mode like abort, fast interrupt request, supervisor mode, system and undefined. And 1 privileged mode which is not a privileged mode, that is user mode. The processor enters into abort mode when there is a failed attempt to access memory. Fast interrupt request and interrupt request modes corresponding to the two interrupt levels available on ARM processor. Supervisory mode, in this mode that the processor, if after reset, and generally the mode than operating system kernel operating it. System mode is a special version of the user mode that allows full read-write access to the CPSR. Undefined mode is used when the processor encounters an instruction that is undefined or not supported by implementation. The undefined mode used when the processor encounters which is not implementable. The user mode is used for programs and applications. All the 37 registers we can see figure 6. What are the registers are allowed for various modes. Next we will see the banked register. Out of 20 registers are hidden from the program at different times. These registers are called as banked register and are identified by the shading in the diagram file. They are available only when the processor is in a particular mode. The bank registers of a particular mode are denoted by an underlined character postfixed to the mode mnemonic like underscore mode. For example, abort mode has a bank register 13 underscore ABT, R14 underscore ABT and SPSR underscore ABT. Every processor made except user mode can change by writing directly or indirectly for mode bits in the CPSR for change of mode. All processor modes except system mode have a set of associated bank registers that are a subset of the main 16 general purpose registers. A banked register maps one-to-one user mode register. If the processor mode is changed, a banked register from a new mode will replace an existing register. For example, when the processor is in the interrupt request mode, the instruction which is executing till the access of the register, that is for stack pointer R13 and the link register R14. However, these registers are banked registers for interrupt request mode, that is R13 IRQ and R14 IRQ. Whereas in user mode, R13 USR, R14 USR, and these will not be affected by the instruction rendering this register. A program still have normal access to other registers from R0 to R12. The processor mode can change by a program that writes directly to the CPSR, which is a processor core has a privilege mode, or by the hardware when the core responds to an exception or an interrupt. The following exceptions and interrupts cause a mode change, like a reset, interrupt request, fast interrupt request, a software interrupt, a data abort, free fetch abort, and undefined instruction. Exceptions and interrupts suspend the normal execution of the sequential instructions and jump to a specified location. The figure 3 illustrates what happens when the interrupt forces a mode change. The figure shows the code changing from user mode to interrupt request mode. When happens, an interrupt request occurs due to an external device raising an interrupt to the processor core. So now here the CPSR is changed to SPSR interrupt request. R13 will be changed to R13 IRQ. Similarly, R14 will be changed to R14 IRQ. In figure 7, we can see what happens when interrupt forces a mode change. This change causes the user registers R13 and R14 to the banked registers. The user registers are replaced with the registers, that is R13 IRQ and R14 IRQ respectively. Note that R14 IRQ contains the return address and R13 IRQ contains the stack pointer for interrupt request mode. Figure 3 shows a new register appearing in interrupt request mode, the saved program status register, which stores the previous mode CPSR. We already discussed the CPSR mode and it will be copied into SPSR IRQ. To return back to the user mode, a special return instruction is used that instruct the core to restore the original CPSR from the SPSR underscore IRQ and the banks in the user registers, that is R13 and R14. The SPSR can only be modified and read in privileged mode. There is no SPSR available in user mode. The CPSR is not copied into the SPSR when the mode is changing or forced due to program writing directly to the CPSR. The saving of the CPSR only occurs when an exception or interrupt is raised. When power is applied to the core, it starts supervisory mode, which is a privileged mode. Starting in a privileged mode is useful since initialization can be done to access the CPSR and set up the stacks for each other modes. The state and instruction set. The state of the core determines which instruction set is being executed. The ARM, it consists of total 3 types of instructions: ARM instructions, thumb instructions and GIL instructions. The ARM instruction set is only active when the processor is in ARM mode. Similarly, the thumb instructions are active when the processor is in thumb state. Once thumb state, the processor is executing purely thumb 16-bit instructions. You cannot intermingle the sequential ARM, thumb and GIL instructions. The J and T bits in the CPSR reflect the state of the processor. When both J and T bits are equivalent to 0, that indicates the processor is in ARM state and execute ARM instructions. This is the case when the power is applied to the processor. When the T bit is set to 1, then the processor is in thumb state. To change the state, the core execute a specialized branch instructions. The ARM and thumb instruction set features. Instruction set for ARM instructions is 32-bit, whereas for thumb it is 16-bit size. The core instructions are 58 for ARM, 30 for thumb instructions. Conditional execution mostly only for branch instructions. Data processing instruction in the ARM, access to the barrel shifter and ALU, whereas in the thumb mode, separate barrel shifter and ALU instructions. Program status word. In the ARM, we have a read-write in privileged mode, whereas in thumb, no direct access for the PSRs. Register uses the 15 general purpose registers plus program counter, whereas in thumb mode only 8 general purpose registers, 7 high registers plus 1 program counter. So in the CPSR, if T bit is equivalent to 0, it indicates ARM mode. If T bit is equivalent to 1, it is in thumb mode. Next we will see state and instruction set. In ARM Designer introduced a third instruction called as Jajal. Jajal execute 8-bit instructions, and it is a hybrid mix of software and hardware designed to speed up the execution of Java bytes codes. To execute Java byte codes, the J technology plus special modified version of the Java virtual machine is required. It is important to note that the hardware portion of Jelly only supports a subset of the Java byte codes. The rest of the emulated in software. The Jajali instruction is a set of closed instruction set and is not openly available. For Java related applications, to use the instruction, the T bit should be equivalent to 0 and T bit equivalent to 1 in the CPSR. The instruction size is 8-bit. The core instruction says over 60% of the Java byte codes are implemented in hardware. The rest of the codes are implemented in software. So with this, I'll conclude the various registers of ARM processor, various modes, which registers are used for user permissions, which registers are used for special permissions. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.